I'm going to talk through two different approaches to this question. First of all, the way that I did it. First of all, I wrote down my stones, whether they're the color and then the number. Okay, and then I thought, just forget about ordering them for the moment. I just thought about what happens if I have two blue stones, because you have to have at least one. Sorry, not at least. You have to have precisely two that are the same color, because you can't have them all that are the same color, and you can't have them different colors. So you're going to have two. So two blues, one of which is B1. Okay, so I actually wrote these down so I could have B1 and B2. And then I need a different color, but I can't have R3, so I've got to have, say, R1, or I could do it with R2, or I could do it with Y1 or Y2. Right, now actually that's four options. There's going to be another four options if I include B3 instead of B2. I'm going to write them down. Now we obviously don't want to do this for every single stone, but we can use some like the fact that if this is the case for B1, then there's going to be the same number for when you have two of the same color and include B2 or Y1 and so on. That's the argument I'm trying to make. So there's 8 options for this situation. For two blues, one of which is B1. Okay, so apply this to every stone. Then there's going to be 9 times 8 options, except I'm going to get, like when I have B2, I'm going to have the case where I get B1 again. So I'm going to double count using this method. So I need to divide by 2. Double counting. So 9, I don't know, 9 lots of 8. Yeah, I hope that makes sense. So I just want to like explain it again. I've looked at all the possibilities when I have two blues, one of which is B1, but then I could look at all the possibilities when I have two blues and one is B2. I'm going to get 8 options again, and then B3, two blues, but one is B3, 8 options, and then go through all the others. Yellow one, two yellows, one of which is yellow one, that's going to be 8 options. That's why I've done 9 times 8. But like I explained, just going to say it again, I've double counted because when I do B2, for example, I'm going to get the B1 in there as well. So I need to divide by 2 to account for that. Now I'm not quite done because we're not just interested in the what we call the combinations, the different ways we can put the tower in. We are also interested in the different towers we can get. So I also need to think about how I arrange my 3 objects. So this is the number of combinations. And then for each combination, I need to think about the permutations actually. That's the extra bit to the problem. For each combination, there are going to be, we say 3 factorial, or 3 times 2 times 1 permutations. Because there's 3 ways I can pick the top one, there's then 2 ways I can pick the second one, and then there would just be 1 way I can pick the last one. So all the different ways of ordering it. Um, Let me just very quickly say, like if it was A, B, C, then we could get A, C, B, but then we could do BAC, BCA, and finally CAB and CBA. Just systematically working through it, 6 options. I just did that through using the idea of factorials. So overall, now for each one of my combinations, there's going to be 6 permutations. So I need to multiply them. 6 times 9 times 8 over 2. What do they call it? Arrangements. Yes, yeah, let's call it that. And that's going to be 6 times 36. So actually 6 cubed, or 216. Now, I talked about there being 2 ways of doing it, or at least I'm going to show you 2 ways of doing it. This is the way the solutions did it. It's quite nice. I like my way as well, but this is also good. So in the second way, they draw a little grid to kind of illustrate the colors and the numbers. So I like this. And so if you wanted blue 1 and blue 2 and then say red 2, then we could, I guess, tick the boxes. Or if you were thinking about the where they go, I want to deal with the permutation separately. That's just going to be a times by 6 at the end. But if you wanted to think about where they go, then you could do B for the bottom, middle, and top. Okay, so you could use that sort of approach. Now, we know we can't have all the same color. So if we basically said, right, first of all, I'm not going to include the red ones, then we could like cross all of these out. And we also know that we're not allowed a certain, all different numbers. So we could maybe get rid of all the 2s. Okay, so that would be one way of doing this. And if we get rid, there's going to be 9 different ways that you can kind of eliminate all of them. So instead of red, I could get rid of blue. Instead of red, I could get rid of yellow, and then I can do it for all the numbers as well. So that because there's 3 times 3 ones that you can basically eliminate. So I hope that makes sense. So once you've done the elimination, we can think about which ones we actually pick. And let's say I want to pick blue 1 and blue 2 and then yellow 1. Okay, that would be one possibility. Now there's 4 boxes that are empty. Sorry, there's 4 possible boxes that are empty. So actually I can then times this by 4 to give me all the different um, combinations essentially. Now that is the same as my 36 from before. I'm just explaining in a slightly different way and I'm hoping that makes sense. And I've not had to deal with the double counting actually because of the way this has been set up. And then finally, we just have to think about the permutations now. And so if we come back to say BMT, we can just look at the different ways we can arrange these 3 things, and that's going to be my 3 factorial or my 6. And so we get 216 that way. I like this approach a lot. I think particularly for a larger number of colors and numbers, this could work a bit better than my approach, which was to start by listing them. But kind of feel, I mean, I guess I spent more time on this, so I think I've explained my way a bit better than this way, but I hope I've done this method justice. Well done anyway on your attempts here.